Angola, New York, December 18, 1867. The Lakeshore Railway passenger train jumps the rails on a bridge over Big Sister Creek, plunging 42 feet into the frozen ravine below. 49 people burn alive, trapped in wreckage as stoves ignite spilled kerosene. The engineer had signaled for brakes, but physics was faster than human hands. And this is the story of why trains couldn't stop, and the young inventor whose childish toy solved a problem that was killing hundreds of Americans every year: the tyranny of the handbrake. In 1867, stopping a train required a small army of men, risking their lives on top of moving cars in all weather, turning wheels by hand until their muscles gave out, or the momentum finally surrendered. This was not a backup system. This was the only system. When the engineer needed to stop, he pulled a whistle cord to signal the brakemen stationed on top of the cars. These men, exposed to wind, rain, snow, and the constant threat of being thrown off by sudden movements, would then rush to the brake wheels. Each wheel required multiple full rotations to engage the brake shoes against the wheels of that single car. A brakeman in good physical condition could maybe lock the brakes on one car in 30 seconds. A freight train might have 40 cars. A passenger express might have 10 to 15. The mathematics were brutal. Even if you had enough brakemen, and they all heard the signal, and they all reacted instantly, and none of them slipped on ice or lost their grip, there was simply not enough time to engage enough brakes to stop a train moving at speed. The death toll among brakemen was staggering. Industry records from the 1860s show that 1 in every 35 railroad workers died on the job each year. Brakemen suffered the highest mortality rate of any occupation in America. They fell from moving trains. They were crushed between cars during coupling. They froze to death on winter run. They were thrown clear during derailments and collisions. The job was effectively a death sentence you collected in installments, but the casualties extended far beyond the brakemen themselves. Passengers died when trains couldn't stop in time to avoid collisions or navigate curves. Crews died in rear-end crashes when following trains plowed into stopped ones before their brakemen could lock enough wheels. Communities near rail lines lived in constant fear of runaway trains that no amount of human effort could arrest. The fundamental problem was physics. A loaded passenger train might weigh 200 tons or more. At 30 miles per hour, that mass carried enormous kinetic energy. The handbrakes could generate friction, but only as much friction as human muscle could apply through mechanical advantage. And that was never, ever enough. Even worse, the system was asymmetric. The engineer controlled the throttle and could accelerate the entire train, instantly. But he could not stop it. He was dependent on men he couldn't see, working independently, fighting against the same momentum he had created. The gap between the power to move and the power to stop was where people died. Railroad executives accepted this carnage as the cost of doing business. They saw it as an unavoidable feature of railroad operation, like the smoke from the locomotive or the screech of steel on steel. Some even argued that if stopping were too easy, engineers would become reckless, accelerating more aggressively, knowing they could brake safely. The danger, they claimed, enforced discipline. This was the world George Westinghouse confronted in 1868. A world where the most advanced transportation system in human history was still being controlled by medieval technology, where the ability to move at unprecedented speeds was married to a stopping mechanism that would have been familiar to a Roman chariot driver. Something had to change. The question was whether the railroads would allow it to change before the body count became politically intolerable. The young inventor, George Westinghouse, he was riding as a passenger when his train plowed into the rear of a stopped freight. The impact threw passengers from their seats. The damage was minor compared to Angola, but Westinghouse, an engineer by training and temperament, immediately grasped the fundamental flaw in the system. He came from a family of inventors. His father ran a machine shop in Schenectady, New York, where young George had learned to think in terms of mechanical solutions to practical problems. He had already patented a rotary steam engine and a car replacer device for guiding derailed trains back onto tracks. But the brake problem was different. It was not just a mechanical challenge. It was a human impossibility dressed as a mechanical system. Westinghouse understood that no amount of clever gearing or improved brake shoes could solve the real problem. The real problem was that control was distributed across multiple men working independently with no feedback mechanism. Even if you could make the brakes twice as effective, You still needed the brakemen to engage them, and they still couldn't do it fast enough. What he needed was a system where one man, the engineer, could apply braking force to every car simultaneously. This required power that could be transmitted the length of the train instantly and applied uniformly, regardless of how many cars were attached. Steam was the obvious candidate. Railroads already understood steam. Every locomotive ran on it, but Westinghouse rejected it almost immediately. Steam lost pressure over distance. It required insulated pipes. It would condense in cold weather. It was the wrong medium for this application. The answer came from an unlikely source. In 1868, Westinghouse read an article about the construction of the Mont Cenis tunnel through the Alps. The engineers were using compressed air drills to blast through solid rock. The article mentioned that compressed air could be transmitted long distances through simple iron pipes without significant loss of pressure. Compressed air could travel through pipes the length of any train. It would not freeze, it would not condense. It required no insulation. And most importantly, it could be compressed on the locomotive using existing steam power and distributed to every car through a continuous brake line. Westinghouse spent the winter of 1868 designing the system in his head and on paper. By spring of 1869, he was ready to build a prototype. He used his inheritance to fund the construction. The system had to accomplish three things simultaneously: generate compressed air on the locomotive, store it in reservoirs on each car, and convert that air pressure into mechanical force that would push brake shoes against the wheels. The genius was in the simplicity. Each car would have its own air reservoir constantly recharged from the main line. When the engineer wanted to stop, he would open a valve that allowed compressed air to flow from the reservoirs into brake cylinders. The air pressure would push pistons that engaged the brakes. More importantly, the system was proportional. A small release of pressure meant light braking. Full release meant emergency stopping. The engineer could modulate the brake force across the entire train with the movement of a single valve. The system explained the compressed air brake system. Westinghouse, patented in 1869, was elegant in its mechanical simplicity. A steam-driven air compressor mounted on the locomotive compressed air to 70 to 90 pounds per square inch. This compressed air flowed through a main brake pipe that ran the length of the train, connecting every car. Each car carried its own auxiliary reservoir, a steel tank that stored compressed air at line pressure. When the system was charged and the brakes were released, this reservoir was constantly being recharged from the main pipe, ensuring that every car had its own supply of pressurized air ready to deploy. The brake mechanism itself was ingenious. Each car had a brake cylinder connected to a triple valve, Westinghouse's key innovation. This valve responded to changes in pressure in the main brake pipe. When the engineer wanted to apply the brakes, he reduced pressure in the main pipe. The triple valve sensed this pressure drop and opened a passage allowing compressed air from the car's auxiliary reservoir to flow into the brake cylinder. The brake cylinder contained a piston connected to a series of levers and rods that pushed the brake shoes against the wheels. The force was substantial. A single brake cylinder could generate thousands of pounds of pressure, far more than any brakeman could apply by hand. And because every car had its own cylinder and reservoir, the braking force was distributed uniformly across the entire train. To release the brakes, the engineer restored pressure to the main pipe. The triple valve sensed the pressure increase and reversed its position, venting the brake cylinder to atmosphere, while allowing the auxiliary reservoir to recharge from the main pipe. The brakes released smoothly, and the system was ready for the next application. But Westinghouse had included something that would prove more important than the braking mechanism itself. He had designed a fail-safe system. In a handbrake train, a broken coupling or a separation between cars meant disaster. The separated cars would continue rolling with no way to stop them. In Westinghouse's system, any break in the airline caused an immediate loss of pressure in the main pipe. The triple valve sensed this pressure drop and automatically applied the brakes on every car. This meant that the brakes automatically engaged if the train separated, if the airline ruptured, if the compressor failed, or if pressure was lost for any reason. The system defaulted to safe. This single design decision would save more lives than any other feature. In April of 1869, Westinghouse convinced the Panhandle Railroad to let him test his system on a 4-car passenger train. The demonstration took place outside Pittsburgh. Railroad officials, newspaper reporters, and curious onlookers gathered to watch what many expected would be an expensive failure. The engineer accelerated the train to 30 miles per hour. Then Westinghouse signaled for an emergency brake application. The train stopped in 200 feet. The observers checked their watches and their measurements. By handbrake, the same train at the same speed would have required at least 600 feet. Westinghouse had just demonstrated a 3-to-1 improvement in stopping distance using a system that required no brakemen on top of the cars and could be controlled entirely by the engineer. The test was a mechanical success, but mechanical success and market adoption are different battles entirely. The wall of resistance. The railroad executives who witnessed Westinghouse's demonstration did not break into applause. They broke into laughter. Commodore Cornelius Vanderbilt, the most powerful railroad magnate in America, dismissed the air brake as a childish toy. When Westinghouse requested a meeting to demonstrate the system on Vanderbilt's New York Central Railroad, Vanderbilt reportedly told his assistant, "I have no time to waste on fools." The resistance was not ignorance, it was calculation. The railroads looked at Westinghouse's invention and saw a threat to everything they had built. First, there was the cost. Installing air brakes on a single locomotive and its cars required significant capital investment. Air compressors, pipes, valves, cylinders, and reservoirs had to be purchased and installed. The railroads had just spent millions building their networks and buying rolling stock. Now, some 23-year-old was telling them their equipment was obsolete and needed expensive modifications. Second, there was the operational disruption. Converting a railroad to air brakes could not happen gradually. It was all or nothing. A train with both air brake cars and handbrake cars was worse than a fully handbrake train because the stopping characteristics were unpredictable. This meant railroads would need to pull entire fleets out of service for retrofitting, losing revenue during the conversion. Third, there was the maintenance concern. The handbrake was simple: wheels, rods, chains, and friction shoes. Any blacksmith could repair it. Any brakeman understood it. The air brake was complex. It had moving parts, seals, valves, and pipes. It required specialized knowledge to maintain. Railroad superintendents worried that this complexity would lead to failures in remote locations where help was not available. But beneath these practical objections lay a deeper psychological resistance. The railroads had built an entire operational culture around the handbrake. They had training programs for brakemen. They had salary structures. They had protocols and procedures and decades of institutional knowledge. The air brake threatened to render all of this obsolete. More fundamentally, it threatened to shift power from the railroad companies to an outside inventor. If they adopted Westinghouse's system, they would be dependent on his patents. They would need to pay him royalties on every car they equipped. They would lose control over a critical aspect of their operations. The executives also argued that the air brake would make engineers lazy and reckless. With the ability to stop quickly, they would take more risks, accelerate more aggressively, and generally operate less conservatively. The danger of the handbrake system, they claimed, enforced discipline. This argument revealed how deeply the railroads had internalized the carnage. They had convinced themselves that danger was not a bug, but a feature, that the deaths of brakemen and passengers were an acceptable price for safe operation. It was a spectacular example of the sunk cost fallacy merged with institutional inertia. Westinghouse faced a wall of coordinated resistance. Railroad presidents talked to each other. They agreed that the air brake was unnecessary. Some went further, suggesting that it was dangerous, that it would fail at critical moments, that it would give engineers false confidence. The Pennsylvania Railroad did agree to test the system on a limited basis. They equipped one passenger train and ran it for several months. The results were remarkable. Stopping distances were dramatically reduced. Brakemen no longer needed to risk their lives on top of cars. Passengers reported smoother stops, but the railroad declined to expand the program. The official reason was cost. The unofficial reason was that success would force them to retrofit their entire fleet. For 3 years, from 1869 to 1872, Westinghouse struggled to gain traction. He improved his design, added redundancies, simplified the maintenance requirements. He published data showing the safety improvements. He offered to install systems at reduced cost just to prove the concept. The railroads remained unmoved, but momentum was building in an unexpected direction. The public was becoming aware that railroad accidents were preventable, that technology existed to make trains safer, and that the railroads were refusing to adopt it for financial reasons. Newspaper editors began asking uncomfortable questions. How many more Angolas would happen before the railroads prioritized safety over profit? Westinghouse needed a demonstration so undeniable that resistance would become politically impossible. He needed to prove that his childish toy could save lives in conditions that the handbrake could never survive. The demonstration that changed minds. The breakthrough came on a spring day in 1876 near Pittsburgh. The Pennsylvania Railroad had grudgingly agreed to another test, this time with higher stakes and more witnesses. They assembled a full passenger train, 8 heavy cars loaded with railroad officials, engineers, newspaper reporters, and invited skeptics. The test was simple but dramatic. The engineer would accelerate to speed, then encounter a simulated emergency. An obstacle would be placed on the tracks ahead. The engineer would apply emergency braking, and the observers would measure the stopping distance. If the air brake worked as Westinghouse claimed, the train would stop before striking the obstacle. If it failed, everyone would witness a collision. The train accelerated to 40 miles per hour, faster than the typical operating speed of the passenger trains in that era. At a predetermined point, a red flag was waved. The engineer immediately applied full emergency braking. The observers felt the brake force hit simultaneously across all 8 cars. There was no delay, no sequential engagement, no hoping that brakemen on top of cars had heard the signal. Every wheel locked. The train shuddered and scraped and howled in protest. It stopped in 260 feet. The obstacle on the tracks was still 50 feet ahead. The observers checked the math. A handbrake train at the same speed would have required at least 800 feet to stop, possibly more, depending on how quickly the brakemen responded. Westinghouse had just demonstrated a 67% reduction in stopping distance, but the real revelation came when they examined the equipment after the stop. Nothing had broken. The airline was intact. The valves had functioned perfectly. The system was ready to be recharged and used again immediately. This was not a fragile laboratory experiment. This was a robust industrial system that could handle emergency conditions and remain operational. Word of the Pittsburgh demonstration spread through the railroad industry. A few forward-thinking executives began to reconsider their resistance. The Burlington Railroad, always more innovative than its competitors, agreed to equip a complete passenger train with Westinghouse air brakes and run it in regular service. The Burlington test was the beginning of a slow conversion. Other railroads watched and waited. They wanted to see if the system would hold up under daily operation, through winter cold and summer heat, with real passengers and real schedules. The Burlington train ran for 2 years without a single brake-related incident. Stopping distances remained consistently short. Maintenance costs were lower than expected. Passenger comfort improved because the engineer could modulate brake force smoothly rather than relying on the violent, jerky action of handbrakes being applied car by car. By 1878, several major railroads had begun limited adoption. They equipped their premier passenger trains, the routes where safety and passenger comfort were most visible. But freight remained stubbornly committed to handbrakes. The economics for freight were different. Freight trains were longer, the retrofitting cost higher, and the public pressure lower. No one protested when a freight brakeman died. That was just the job. The partial adoption created a strange transitional period. Passenger trains became dramatically safer, while freight trains remained death traps. Brakemen on mixed-service railroads learned which assignments meant safety and which meant mortality risk. The union pushed for universal air brake adoption, but railroad management resisted. What finally broke the deadlock was not economics or engineering arguments. It was blood. The crash that forced the issue. October 10th, 1888. A Lehigh Valley Railroad excursion train carrying 400 people, mostly Sunday school children and their families, descended a long grade approaching a sharp curve. The engineer signaled for brakes. The brakemen scrambled to their wheels, but the train was heavy and the grade was steep. The handbrakes could not generate enough friction to control the descent. The train entered the curve at 40 miles per hour. The wheels screamed. The cars began to lean. Then the coupling between the locomotive and the first passenger car snapped under the lateral force. The locomotive, now detached, continued around the curve and stopped safely ahead. The passenger cars, suddenly freed from the engine's weight and momentum, continued straight. They left the rails and plunged down an embankment into a ravine. The wooden cars shattered. Stoves and kerosene lamps ignited the wreckage. 64 people died. 58 of them were children. The nation reacted with fury. This was not a crew dying in a freight yard accident. This was not a collision that could be blamed on human error or bad luck. This was children burning alive because the railroad had refused to install technology that could have prevented the disaster. Newspaper editorials demanded action. The New York Times wrote that the railroads had murdered the victims of Mud Run through their obstinate refusal to adopt modern safety equipment. Clergy preached sermons condemning the greed that valued profits over children's lives. Mothers formed safety organizations demanding mandatory air brakes. The political pressure became overwhelming. State legislators introduced bills requiring air brakes on all passenger trains. Railroad executives, sensing the mood, suddenly discovered that air brakes were not childish toys after all. They were, in fact, perfectly sensible safety improvements that the railroads had been planning to adopt anyway. The conversion happened with stunning speed. Within 3 years of Mud Run, virtually every passenger railroad in America had equipped their trains with Westinghouse air brakes. The man who Vanderbilt had called a fool was now courted by the same executives who had mocked him. His company, Westinghouse Air Brake Company, could barely keep up with the orders. The safety impact was immediate and dramatic. Rear-end collisions dropped by 70%. Derailments caused by inability to control speed declined by similar margins. The death rate for railroad passengers fell by more than half. Brakemen were reassigned from roofs to inside the cars. The image of men running across the tops of moving trains slowly faded into memory. But freight railroads still resisted. The economics were harder to justify. Freight trains were longer, often 40 to 60 cars. Equipping them with air brakes was expensive, and unlike passengers, freight could not organize politically or demand safety measures. The railroad unions tried to force the issue, but management held firm. If the government wanted freight trains to have air brakes, the government would need to mandate it. The cascade of adoption. The conversion of passenger railroads created an unexpected economic cascade. Suddenly, there was a massive installed base of air brake equipment. Maintenance facilities had been trained. Engineers understood the system. The infrastructure existed. Converting freight trains from this starting point became dramatically cheaper than it would have been starting from scratch. More importantly, the operational advantages became undeniable once railroads experienced them firsthand. Trains with air brakes could run faster because they could stop quicker. Schedules became more reliable because brake-related delays vanished. Insurance companies, seeing the accident data, began offering lower premiums for air brake trains. The railroads that had converted their passenger fleets began quietly converting their freight operations. Not because they had suddenly developed consciences, but because the economics had reversed. The cost of retrofitting freight trains was now lower than the cost of maintaining two separate systems, and the reduced insurance premiums offset the capital investment within a few years. By 1890, an estimated 60% of American railroad cars were equipped with air brakes. The holdouts were primarily small regional railroads and short-line operations that did not have the capital for large-scale improvements. The Union saw its opportunity. The Brotherhood of Locomotive Engineers and the Brotherhood of Railroad Trainmen joined forces to demand federal legislation. They had data now. Railroads with air brakes had accident rates far below those still using hand brakes. The connection was undeniable. Hand brakes killed people. Air brakes saved them. Any railroad still using hand brakes was knowingly choosing mortality over modernization. The public, still traumatized by Mud Run and a string of smaller accidents, supported federal intervention. Congressmen from railroad districts faced pressure from constituents who had lost family members in preventable accidents. The political will existed. The question was whether Congress would actually pass meaningful safety legislation or produce the usual toothless compromise. The Federal Hammer. On March 2, 1893, President Benjamin Harrison signed the Safety Appliance Act into law. The legislation was brief and absolute. All trains engaged in interstate commerce must be equipped with automatic couplers and air brakes by January 1st, 1898. No exceptions, no extensions. Railroads that failed to comply would be barred from interstate operations. The law was revolutionary not just for what it required, but for how it was enforced. Previous railroad safety legislation had been advisory. Railroads were encouraged to adopt safety measures, but faced no penalties for ignoring them. The Safety Appliance Act was a federal mandate backed by the full power of the Interstate Commerce Commission. The 5-year compliance window was intentional. It gave railroads time to retrofit their existing equipment and ensured that all new rolling stock would be built to the new standard from day one. It also prevented railroads from claiming hardship due to sudden costs. 5 years was enough time to depreciate old equipment and budget for replacements. The law transformed Westinghouse from a controversial inventor into an industrial titan. Every railroad in America would need to purchase his equipment or license his patents. The Westinghouse Air Brake Company became one of the most valuable manufacturing concerns in the nation. George Westinghouse, the fool who wasted Vanderbilt's time, was now a millionaire whose technology was mandated by federal law. But more important than Westinghouse's fortune was the cultural shift the law represented. The federal government had declared that worker safety and public safety took precedence over corporate profit. Railroads could no longer choose to operate unsafe equipment simply because it was cheaper. The invisible hand of the market had been restrained by the very visible hand of federal regulation. By January 1st, 1898, every major railroad in America operated with air brakes. The conversion was complete. Handbrakes remained on cars only as backup systems for use in yards and sidings. The era of brakemen risking their lives on top of moving trains was over. The safety statistics from the following decade vindicated every claim Westinghouse had made. Railroad fatalities dropped by 75%. Collisions and derailments declined proportionally. Insurance companies recalculated their risk models. The railroads, now forced to operate with air brakes, discovered that their initial cost objections had been wildly overstated. The safety improvements reduced accident costs so dramatically that the systems paid for themselves within 3 years. The executives who had mocked Westinghouse's childish toy never apologized. They simply rewrote the narrative. Now they had always supported air brakes. Now they took credit for the improved safety record. Now they marketed their air brake trains as evidence of their commitment to passenger welfare. Legacy and modern impact. Walk to any railroad crossing today and watch a freight train pass. Those distinctive hissing sounds as the train slows are Westinghouse's air brake system, refined and improved but fundamentally unchanged from his 1869 patent. The compressed air flowing through brake lines, the fail-safe design that applies brakes when pressure is lost, the proportional control that allows the engineer to modulate brake force. All of it descends directly from that first demonstration outside Pittsburgh. But the legacy extends far beyond railroads. Every semi-truck on American highways uses air brakes. Every city bus, every large commercial vehicle. The principal Westinghouse discovered that compressed air could transmit force reliably and safely over long distances became the foundation for vehicle braking systems across every mode of transportation that moves heavy loads. The fail-safe design philosophy, that systems should default to safe states when they fail, became standard engineering practice. Modern aircraft, nuclear power plants, and industrial machinery all incorporate this principle. Engineers call it fail-safe by design, but they are applying Westinghouse's insight from 1869. The Safety Appliance Act established the precedent that government could regulate private industry for worker and public safety. Every subsequent federal safety regulation, from mine safety to workplace protections to automotive safety standards, traces its legal lineage to the decision that Congress could mandate air brakes on trains. The death toll among railroad workers dropped from 1 in 35 per year in 1867 to 1 in 400 by 1910. Brakemen, who had suffered the highest occupational mortality rate in America, saw their job transform from a death sentence to a skilled trade. Thousands of men who would have died on top of moving trains lived to retire instead. The passenger safety improvements were equally dramatic. Before air brakes, railroad accidents killed approximately 800 Americans per year. By 1910, despite dramatically increased rail traffic, That number had fallen below 200. The air brake did not eliminate railroad accidents, but it eliminated the specific category of accidents caused by inability to stop. Economic historians estimate that the air brake saved at least 15,000 American lives between 1890 and 1920. That is a conservative estimate that counts only direct fatalities prevented. It does not account for injuries avoided, property damage eliminated, or the economic value of faster, more reliable rail service. The irony is inescapable. The railroads that fought air brake adoption for decades would not have survived the 20th century without it. The speeds required for competitive service, the traffic densities needed for profitability, the safety standards demanded by insurance companies all required air brakes. The technology they dismissed as unnecessary became the foundation for everything they built. Westinghouse himself never stopped inventing. He went on to pioneer alternating current electrical systems, challenging Thomas Edison's direct current monopoly. He developed railway signaling systems, industrial steam turbines, and hundreds of other innovations. But the air brake remained his most important contribution. It was the invention that proved a single person with a better idea could force an entire industry to change, even when that industry was the most powerful economic force in America. Angola, New York, December 18th, 1867. 49 people died because physics moved faster than human hands could respond. 26 years later, on January 1st, 1898, every train in America could stop on command because one young inventor refused to accept that the massacre was inevitable. The childish toy saved an industry from itself. If you want more stories about the inventions that changed everything, despite those who said they never would, subscribe because the resistance to progress never stops, but neither does the progress.